Hi, this lesson is on continuity. So the definition is that a function is continuous at a number that we're calling a if the limit as x approaches a of f of x equals f of a. So basically, you can say that a function is continuous at a particular value that we're calling a as long as the limit value as x approaches a and f of a are equal. That means that a must be in the domain, and the fact that the limit exists means that the limit has to converge to the same number from the left side and the right side of a. So remember, the definition of the limit means that your limit has to approach the same value for a left-hand limit and a right-hand limit. So what that means is that a small change in x near a represents a relatively small change in f of x. So you're not going to see big jumps in the graph. And from a very simplistic way, the way to describe it, the way I would describe it like to a child is if you can draw the graph without picking up your pencil, it would be continuous. If you need to pick up your pencil to go to a different piece of the graph, like if it's a piecewise function, sometimes you need to do that when you have asymptotes. You won't be able to draw it continuously. So here are some examples of how to identify a function that's continuous, and then we'll talk about discontinuities. So just to spell it out more clearly, if f of x is continuous at a, then f of a is defined, which means a has to be in the domain of the function. The limit must exist, and therefore that means that the left-hand limit and the right-hand limit are equal. And finally, the limit value and the function value must be the same in order for the function to be continuous. So here's an example on the right here in orange. So at 0, we can see that this graph is continuous because the limit as x approaches 0 is -2. So as you get closer and closer to 0, your function value is approaching that value. F of 0 is equal to -2, and therefore f of x is continuous at 0. And in fact, based on the picture, it looks like this graph would be continuous over all real numbers because there's no gaps or jumps or asymptotes in this graph. So you can have a graph that is considered to be continuous from only one side. So if it's continuous from the right at a, then the right-hand limit and the function value are equal. So sometimes that occurs where it's not continuous over at a itself, but it could be continuous from one side. So for example, this graph, because it looks like it's only defined from 2 to infinity, its right-hand limit is approaching 3, and f of 2 is also 3. So this would be considered to be continuous from the right at 2. It's not continuous from the left because there's nothing in this graph to the left of 2. Like everything from this point forward, there's nothing defined. So similarly, it could be continuous from the left if the left-hand limit and the function value are equal. So an example like here, the limit as x approaches 1 from the left is approaching the value of 4, and f of 1 equals 4. So therefore, this is left continuous. So let's determine if this function, 2x cubed minus 3x, is continuous at x equal to -2. So it's important to recognize f of x as a polynomial function. Polynomial functions have exponents that are whole numbers. So this is to the third power, this is to the first power. So no negative exponents, no radicals. When it's a polynomial function, your function will be continuous over all real numbers. So it will certainly be continuous at -2. But how do we prove that? Well, we have to go back to use this definition above. So x equal to -2 is in the domain. Again, it's a polynomial function. All real numbers are in the domain. And we know that the limit, when we evaluate the limit as x approaches -2, we can evaluate that by direct substitution. And when you plug the -2 in, you get that the limit is -10. When you evaluate f of -2, because it is in the domain, it is also equal to -10. When the limit value and the function value are equal, then you can conclude that your function is continuous at -2. So if you're asked to prove if a function is continuous at a particular value, you basically have to show that the limit exists and the function exists and they are both equal. All right, so we're going to graph this piecewise function, x equal to x plus 1 for values of x greater than or equal to 2, and it's equal to x squared minus 1 for values of x less than 2, and we want to determine if it's continuous at 2. All right, so let's graph it first. So I graphed the linear part of it, x plus 1 in orange, and so that's this piece right here. So because it's only defined for values of x greater than or equal to 2, you want to plug in 2, and that gives you 3. That's this orange point right there. And then plug in something greater than 2, such as 3, which is right here. So at 3, x is 4, y is 4. So, and then draw your line going towards the right because it's greater than 2. Then we have to graph the parabola. And with parabolas, you want to make sure that you show the vertex if it falls within the domain. So for this, we want values less than 2. The vertex is at 0, -1, so that is less than 2. So that's right here. But you should also plug in 2. And when you plug in 2, you get a value of 3, which is actually this point right here. Now it's open for the parabola, but remember the line made that closed. So the closed point supersedes the open one. So that's why it's remaining this as this solid orange point. And then, the parabola is U-shaped and it's going upward. So there's your parabola drawn here in this bluish green color. So from the graph, you can see that if I needed to graph this, I could graph this this piecewise function continuously. I can draw this. I can actually go like this and then draw the line without picking up my pen. This will be continuous, but we need to prove it. So we want to first evaluate our limit. So let's evaluate the right-hand limit. The right-hand limit means that I'm approaching 2 from the right. Remember, on the right side, that's greater than 2, I'm looking at the line. So that's what I need to plug into. I need to substitute 2 into the value of x for x plus 1, and that gives me a value of 3. Now I need to do the same thing from the left side of 2. When I'm on the left side of 2, I'm on the parabola. And just like in the last example, you can do this by direct substitution. So if I plug in 2 here, you also get a value of 3. So therefore, your limit exists. Your limit is 3. Your function also exists at 2. So when x is equal to 2, that's where it's defined as the line. You plug in the 2 into the x plus 1, you also get 3. So you have a limit value that's 3. You have a function value that's 3. So then you can conclude that your function is continuous at 3. So we can talk about continuity over a domain, or you can talk about continuity over just an interval of values. Regardless of how you're considering the continuity, you're always checking for continuity by evaluating the limit at a particular value and then evaluating the function at that same value. And when they are equal, they are continuous. If they are not equal or it's not in the domain, then it would not be continuous. So let's go back to this concept of left-hand continuous and right-hand continuous. So let's determine if g of x is left continuous, right continuous, or neither at x equal to 0 for, again, another piecewise function, g of x equal to the square root of 3x plus 4 for values of x less than 0, and negative x squared minus 2 for values of x greater than or equal to 0. So let's make sure that this actually works for values of x less than 0. In other words, do we get a real number? So if I plug in a value less than 0, like negative 1, that will give me a positive result. But once I go beyond negative, actually a little bit more than that, if I solve this, set it equal to 0, negative 4, x is equal to negative 4/3. At negative 4/3, my radical is going to be equal to 0, which is okay. But anything less than negative 4/3 is going to be a problem because then I'll have an imaginary result. So in order for this to make sense in terms of real numbers, my domain here has to be from negative 4/3 less than or equal to x, which is less than 0. And then we'll only be dealing with real numbers. Here, this is fine. This is a polynomial. This is defined for all real numbers, so x greater than or equal to 0 is good. So let's look at what happens as x approaches 0 from the left. When I'm on the left side of 0, I'm looking at the radical portion of this. I can apply direct substitution in here. So when you plug in the 0, you'll get the square root of 4. So the limit value from the left is 2. When I'm considering the limit on the right, to the right of 0, that's when it's greater than or equal to 0. That's then the parabola. By direct substitution, I plug that in, and here I get negative 2. What that means is that the limit does not exist. Since the limit does not exist, that means it's not continuous at 0, but we can still determine whether it's left or right continuous. So let's see what happens when I actually plug in 0. When I plug in 0 into g, again, you're looking at this piece because that's where it's greater than or equal to 0. So I'm plugging into the parabola. I get negative 0 squared minus 2, which is equal to negative 2. Notice that the function value and the limit value here are equal, and this is the right-hand limit because of 0 from the right. So therefore, since the right-hand limit is equal to g of 0, then we say that g of x is only right continuous at 0. Okay. So here's a theorem regarding continuity. So if f of x and g of x are continuous at a and c is a constant, then the following is also continuous. So if you're adding two continuous functions, that sum will also be continuous. The same is true when you're subtracting two continuous functions. If you're multiplying a continuous function by a constant c, that just becomes a coefficient of the function, so the c times f of x is also continuous. The product of two continuous functions is still continuous, and the quotient of two continuous functions is still continuous as long as g of a is not equal to 0, because again, division by 0 is undefined. So this is also true when we're talking about composite functions. If f of x is continuous at some value b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is just equal to f of b. So in other words, you can take the limit of the inner function and then evaluate the function where that limit exists. All right, so let's talk about discontinuities. So a function that is not continuous at some value a is considered to be discontinuous at a, and those values are called discontinuities. And there are three types of discontinuities. The first type is called a removable discontinuity. And a removable discontinuity exists when the limit exists, but the limit and the function value are not the same. And so that could be because the limit exists and the function does not exist, or the limit exists and the function has a different value. So, for example, I can evaluate this limit, and I could do that with the techniques we learned in previous sections. I could factor it and then do direct substitution, and you would get that your limit is a half. But this function does not exist at 1 because it's undefined. You would be dividing by 0. So here's a graph of what that would look like. The graph looks like it's continuous everywhere except at the value of 1. And at the value of 1, there is an open circle. And that open circle actually has the value of 1 comma 1/2, the value of the limit. So that's helpful when you're graphing functions to know what the limit value exists when you have a removable discontinuity, so that you know exactly where to plot the open circle. Another type of discontinuity exists when the limit as x approaches a from the right and the limit as x approaches a from the left exists, but they are not equal. So you could have a limit that doesn't exist because they are different. But basically, we call this a jump discontinuity because on the graph, it really looks like you're jumping from one piece of the graph to another piece. So I have one piece graphed here in this hot pink color and another piece graphed in this lighter blue, and that represents this function here. So it's a piecewise function. Our f of x is a constant of 5 for values of x greater than or equal to 3. So that's this horizontal line here. And the other one is negative 2x, which is also a line. And we want to plot it starting at 3. So when x is 3, y is, when you plug that in here, y is negative 6. So that's this open circle here because it's less than 3. And then you want to plot something less than 3. I think I plugged in a 0. So when you plug in a 0, another point is here at the origin. Connect the open circle and that point and go towards upwards and towards the left. And there's your piecewise function. This is f of x. So you can see that is the limit as x approaches 3 from the right is 5. So on the right side of 3, my graph is going towards 5. But on the left side of 3, my graph is approaching negative 6. My limit values are different. My function exists. It actually exists at 3 is equal to 5. So not only can we say this is a jump discontinuity, but you can also say that it is right continuous at x equal to 3, and that's because the right-hand limit and the function value are equal at 3. So it is a jump discontinuity, but it is only right continuous at 3. And the last type of discontinuity is called an infinite discontinuity, and that's when you approach your limit either from the left or the right or both, and your function is either going towards positive or negative infinity. And so typically those will represent vertical asymptotes, and vertical asymptotes are shown on a graph as a vertical line that's dashed. So here are 3 different examples. So this is the graph for tangent. I showed a couple of periods of it. Tangent has vertical asymptotes at pi over 2 in every pi units to the left and right. So negative pi over 2, 3 pi over 2, etc. So if I wanted to know what was going on as x approaches pi over 2 from the left, well, when I'm on the left side of pi over 2, this is going towards infinity. So that also shows that this is an infinite discontinuity. There is a break in the graph at pi over 2. If I similarly did this problem and I asked for the limit as x approaches pi over 2, let's say from the right, meaning this side of pi over 2, then my graph would be going towards negative infinity. Either way, it shows that pi over 2 has an infinite discontinuity. Second example is 1 over x. That's called the reciprocal function. This has a discontinuity at 0. Again, 0 is not in the domain. And you can see on the graph, here's the graph of 1 over x. As you approach 0 from the right, your graph is approaching infinity. When you approach 0 from the left, it is going towards negative infinity. So in both cases, both looking at it from the right and from the left, you can see that I have an infinite discontinuity at 0. And here's one more example, ln of x. Remember, ln of x has restrictions on the domain. The domain is from 0 to infinity. It is not defined at 0, and it's not defined for negative values. So it only makes sense to consider your limit from the right. There is nothing on the left of 0 for this graph. So as you approach 0 from the right side, so I'm on the right side of 0, and you look at what the graph is doing, this is going towards negative infinity. So therefore, it's discontinuous at 0. And so here's a reminder. Domain for ln is from 0 to infinity, but the range is negative infinity to infinity. Okay, so that's the 3 types of discontinuities. So let's talk about how to identify discontinuities and label each one. So determine where this rational function f of x equal to x squared minus 4 over x squared minus 3x plus 2 is discontinuous and label each type of discontinuity. So in order to do that, we definitely need to factor, and they're both factorable, both the numerator and the denominator. So factor the numerator, it's the difference of perfect squares. Factor the denominator, and you get x minus 2, x minus 1. But when I factor, you can see that the x minus 2's cancel. When that happens, that's something special in terms of what's going on with the graph. That factor where they cancel is going to end up being a whole. But we know immediately from this denominator that I have 2 restrictions to the domain, at 1 and at 2. Because when x is 1, I will get 0 in the denominator, and when x is 2, I will get 0 in the denominator, and we know that that is undefined. So I have 2 discontinuities, at 1 and 2, but I have to figure out what type they are. Are they removable, a jump, or infinite? And they don't both have to be the same. So let's consider what's going on at 1. So once I cancel my common factor, f of x is this simpler rational expression, x plus 2 over x minus 1. So I'm going to evaluate the limit as x approaches 1. But as x approaches 1, I know that I can't just plug it in, because again, I'll get 0 in the denominator. But I can do this sign analysis, figure out what's going on. And it will have different behavior whether I'm on the right or on the left. So again, imagine plugging in a number close to 1 that's greater than 1, something like 1.0001. And if you plug that in, I'm going to be dividing by a very small positive number, a number very close to 0 that's positive. And when you're dividing by a very small positive number, the whole thing is going to go to infinity. Okay, which already shows that at 1, I have an infinite discontinuity. But let's look at it from the left side. So right here, when I'm on the left side of 1, a potential number that I could plug in to the left side of 1 would be something like 0.9999. If I plug that in there, I'm going to get a negative number that's very close to 0, like negative 0.0001. And again, dividing by a number like that makes the whole thing become a very negative number. So this would be approaching negative infinity. So whether I'm on the right side of 1 or the left side of 1, my function is going to either plus or minus infinity. That means that it's discontinuous at 1 and it is considered to be an infinite discontinuity. That means I'm going to have an asymptote there, a vertical asymptote. Now we have to figure out what's going on at 2. Might not necessarily be the same behavior like I mentioned before. Because these factors cancel, the x minus 2 and the x minus 2 cancel, I know there's going to be a hole there. So we need to figure out, what is this limit? What is the limit as x approaches 2 of x plus 2 over x minus 1? In this case, I can apply direct substitution because that x minus 2 factor canceled before. So when I plug in the 2, I'll get 2 plus 2 over 2 minus 1, which tells me that my limit is 4. What that means is, at the point 2, 4, I will have a hole in the graph, an open circle. And when you have a limit that exists, so this limit exists, but the graph does not exist, that is considered to be a removable discontinuity. So this one had both an infinite and a removable discontinuity. Right, that's it for this lesson. Give the homework a try. Good luck.